The second talk in this morning session is Jeremie Unterberger from
Université de Lorraine, Nancy.
Sorry, okay. And anyway, he'll tell us about the KPZ equation, large-scale behavior.
Yeah, thank you. Thank you for the introduction. Let me thank the organizer once again very warmly for this wonderful conference, also for the dinner tonight, and particularly grateful also that we didn't have too much wine yesterday, so we can all listen today. So the title is Large-Scale Limit of the KPZ Kardar-Parisi-Zhang equation in dimension larger than 3. So compared to what Ajay was saying just a few minutes ago, it's exactly the opposite regime. So we are supercritical, okay? So I will not speak only about the KPZ equation, but about class of equations which are all supercritical. And so we're not interested in the ultraviolet limit, which is, I need an ultraviolet cutoff, fixed cutoff, SK0 say, okay? No hope to go beyond. But what I want to describe is the infrared or large-scale limit, if you want, of the equation, as a statistical physicist would do. So you have a fixed mesh or lattice or anything, or cutoff, in the ultraviolet, and you want to understand the large-scale limit. Right, so this is joined on a base work with Jacques Magnin, and has been published in the Journal of Statistical Physics. Before I speak about the KPZ equation, I wanted to give some general ideas, somewhat introductory way, hopefully pedagogical. So general ideas about how to renormalize using my methods, a method of Jacques Magnin, so constructive field theory methods, for a class of dynamical models. So it's basically about dynamical renormalization. I know that many mathematicians have been working on dynamical renormalization, but this dynamical renormalization things, I mean, using constructive methods has not been developed so much. So this is kind of new from that perspective. So I want to consider a class of dynamical models that could be stochastic PDEs or possibly also interacting particle systems, who knows, of this form. So you have a function phi of t and x. So this is not time derivative. This is for fixed time, okay? Solution at time t is given by a semigroup. This is one way to describe things. So phi is a function of t and x. So it's a function from r plus to cross rd, so maybe scalar, for instance, okay? And so capital phi is a semigroup, by which I mean that phi of t prime composed with phi t prime, yeah, that's correct, is phi t second. That may not be too specific for the moment, okay? I want phi to depend on noise, some noise. Basically, I will be concentrating on stochastic PDEs, so you can imagine that the noise is some eta or zeta, whatever you call it, which is white noise, space-time white noise, for instance, not necessarily. And the other thing is, the general philosophy is, this depends on a certain coupling constant lambda. And because I'm using perturbation theory, sophisticated perturbation theory, okay, but still perturbation theory, I want the coupling constant to be smaller, maybe less than 1 over 100, something like this, okay? And so this depends on a parameter lambda implicitly, so phi eta is phi lambda eta. And when lambda equals 0, what we have is psi eta, which is linear, a linear semigroup. So I'm studying perturbations of the linear semigroup. And as I said, I want to understand the large scale limit of this kind of flows, right? So let me give you two examples. First example, of course, the KPZ equation. So capital phi will be KPZ with d larger than 3, right? So let me just write down the equation. So psi will be the Edwards-Wilkinson flow, the one that Martin Heyer was mentioning yesterday. Okay, so I want to prove that this flow is in the same universality class as the Edwards-Wilkinson flow, which contrasts strongly with the one-dimensional case, of course. So the equation, the KPZ equation, is of this form. So dt minus nu delta. Usually the solution is called h, not phi, because it's a height. Okay, but h is just like phi. Okay, is lambda. So this is complete constant. Could be squared gradient. Could be also v of nabla h, where v is convex. Well, need to be more specific, but plus noise with a constant or strength coefficient which is positive, which I call square root of d. Okay, so this is phi, and psi is of course the same but with lambda equals 0. So this is a stochastic heat equation. Right. So this is first equation, first example. And the rest of my talk I will be concentrating on this equation with quadratic nonlinearity, right?
You said you have to regularize. How do you regularize?
Everything is regularized at scale 1, say. Okay, so this is white noise with convoluted by some scale 1 truncation. Okay.
But only in space? Only in space or also in time?
Space and time. I mean, time is not necessarily, I imagine, but I added it, regularization time too. Okay, doesn't matter really. So a second example. So a model that was introduced in a very interesting article a long time ago by Garrido, Leibowitz, Mais and Spohn in 90, an article called Long-Range Correlations for Conservative Dynamics. Okay, so they were interested in studying non-equilibrium steady states, NES for short, right? So they started actually from a model of interacting particle systems, AZEP-like, asymmetric exclusion process. So if you know asymmetric exclusion process, you know that it has a stationary measure, which is very simple, which is a tensor product of Bernoulli with some density rho, which is uniform, okay, and which is exactly the same stationary measure as for a symmetric exclusion process, but in the case of the stationary exclusion process, it's an equilibrium measure. For ASEP, it's not equilibrium, but it's only stationary, right? But it's a sort of coincidence. So if you change a little bit the microscopic rules, so allowing, for instance, some jump to next nearest neighbor site, right? Then you will end up with some stationary measure, plausibly, but that won't be of this tensor form, right? So the question was, can we prove that there is some stationary measure corresponding to, well, some generalized ASEP, something like this? So the idea is that you are in more than one dimension, or more than one space dimension, and you have some drift in a certain direction given by a sort of electric field, which explains the A of ASEP, if you want. So it's not symmetric. And so, well, they didn't answer the question, but they built hydrodynamics in larger deviations out of the hypothesis that this stationary measure did exist. So that was joint work with A. Ying and okay, very nice articles. But the theoretical question was not solved. And so they gave a mesoscopic equation which modeled this kind of equations in principle that could belong to this scheme. So, so this time H is called phi, but never mind. So it's minus the divergence of a certain current, and the current. So this is model B in the Hornberg-Halperin classification, if you know it. So never mind, you don't know. So you have a Ginzburg-Landau type Hamiltonian, okay, and yeah. So well, something like phi square plus gradient phi square. I don't want to give details, but the important thing is that you will add to the current something that depends on an electric field with a conductivity that is field dependent. Right. And maybe you have a small lambda here also. And sigma phi, well, if it's field independent, then you only need a Galilei transformation and you get rid of it, okay? But assume it's not phi independent, well, you can also move the linear part. So what's important is the quadratic part. So sigma phi equals phi squared, for instance. Well, this is the kind of equation that you would like to solve, and it's interesting also physically, because what you expect is that you get long range correlations, quite contrast with what you have with a set, for instance. Okay. Right. So what's the general idea to study this kind of equations? Well, here it is. So here's some general plot. So you have phi eta between time t and time t prime. I'm going to write it as telescoping sum. They say that in English also. In sum telescopique.
Telescopic sum.
Telescopic sum. That's correct. So it's not such a long formula. Right. So the idea is, the first term is simply phi eta from time t to time t minus 1 minus phi eta, phi 0 from time t to time t minus 1. Circle composed phi eta. This is first term, okay? Now let me just explain to you what I'm doing. Phi eta is of order 1. Phi 0 is also of order 1. I want to compare the two flows, okay? Because I have good reasons to assume that you can subtract the main part of this term in the large scale limit. So you want to show that this is small in some sense, okay? Not very small, but small enough to be exploited. So this is first term, and then the second term is of this form. Plus, etc. Okay, so of course it's not explicit. So the idea is this I can bound. Okay, but of course this is well, you have to solve it inductively in time or something like this. So this you don't do either. So you have to have a bound on this. So what you do, you apply the scheme once and once again. Okay, you do this perform this decomposition also on these. Phi eta located on the right of the equation, okay? What about this? Well, this looks a little bit different from this, but not too much actually. So when you perform this between time t and time t minus 2 to the j, something like this, where j is a positive exponent, this looks like this kind of subtraction, but in a different scale, in a different time scale, okay? So it should be small as this subtraction, but small for something that is of scale j, which is much smaller, even smaller than this subtraction, okay? Its case like j, okay? Right, so if you want to, so you iterate this expansion, and what you end up is something like this. So you have a sum over time insertions. So m1 less than m2 less than etc. So let me do it like this. So first of all, you have phi 0 between time t and time t minus m1. There no noise, okay? So of course, you want this, well, phi 0 will look like a linear flow if you're fortunate enough without any noise, and so you assume that you can bound this flow even though it's not exactly linear, but it should enjoy more or less the same bounds, more or less, okay? It's just like a propagator, but it's not a non-linear propagator. That's the problem, okay? But heat-like. And then you have some insertion, and this insertion could be phi eta minus phi 0, okay? That's an insertion at time t minus m1. So this is subtraction. Phi eta minus phi 0. And then you proceed inductively. So this is really a Galavotti-Nicolò type representation where these dashed lines mean that you are at the same point, basically, at least same time coordinate, okay, that you iterate. So this is composition of applications, okay. But then if m1 is of order 2 to the j, then I plot this on a j. Well, it's like it has several lines, okay. So this is on line j, okay. So here I'm assuming, since this is at scale k, which is larger than j, that you can see there. Sorry, that was the point. So here, okay, let me just. Okay, so this is kj, this is k, right? So here you are between time t minus m1 and time t minus m2. And what I mean by that drawing is that m1 is of order 2 to the j, and m2 minus m1 is of order 2 to the k, with k larger than j. Right? What?
That's a stupid question. Why do you call it subtraction?
It's phi eta minus phi 0 or something like looks like it.
It's a composite.
No, but you can use this semi-go property for the second term.
Oh, okay. Yeah.
Okay?
Okay. Yeah.
Now, my hypotheses are as follow. So phi eta, let's just assume that you do this on time differences that are of order 1, okay? And then you have some scaling otherwise. But so you want to subtract the two flows, and you start from some initial condition at time t minus m minus 1 that you call h, or h t minus, well, let's just call it h, or f if you want. This is the initial condition, right? And the hypothesis is that it's of order eta restricted to this time slice plus lambda O of f. So it's a kind of stability assumption, and it's not at all obvious if you consider any arbitrary partial differential equation, because it's not linear, okay? Phi is non-linear. So it's difficult if you think, for example, of Euler equation or any hydrogen wave flow, okay? Any small perturbation will grow exponentially, even more than exponentially, it will explode, okay? You cannot expect it to be true in general. However, here we're in a class of Hamilton-Jacobi equations, so where you get some convexity, some comparison principle, maximum principle, and this implies that you can bound subtracted flows. And so they depend on eta. Of course, you have to be much more precise, but that the dependence on the initial condition is small. There's lambda here. So if you want to iterate this, you will take advantage of the small coefficient lambda to say that in some sense it is contracting, a contracting sequence of maps that you can iterate and get bounds that are uniform in time. That's the idea. So this I call stability with respect to the noise. Okay, so this is hypothesis number 1. And then hypothesis number 2, you also require stability with respect to initial condition, which means that if you don't subtract, but compare. I don't want to be very specific, but just want to compare phi eta of f1, well, phi eta t minus m minus 1 with initial condition f1 to phi eta t minus m minus 1 f2. And you want to show something like this, right? Where here instead of f you would have f1 minus f2, something like this. But what I claim is that's a good setting where you can try to take advantage of this decomposition. So what remains to be done essentially? So since this is essentially small, well, yeah?
What would be the right-hand side in the second case?
Okay, let me. So the difference is O of phi eta t minus m minus 1 h1 minus h2 plus lambda O of h1, for instance. Something like this.
You mean f1 minus
yeah, that's f1, sorry, yes. Yeah. Yeah, okay. Yeah, so assuming this is small in some sense that you can iterate. So if you have iterated phi eta minus phi zero composed, then it will give you lambda times lambda times lambda, something like that. So it's a converging geometric series. The problem is that you also have long strands like this with time duration of scale j, for instance, or well, time duration m1, which can be arbitrary from 0 to infinity, right? So what is still needed, and that's the crucial point, is to sum over all insertion points. For instance, here, assuming that this t minus m2 is simply t prime, right? You want to sum over the time location m1, right? And that's a problem because so the idea is, of course, it's much more technical, but so assume t and t minus m2 are fixed, more or less.
I'm sorry, I'm totally confused because I don't really know where these scales came from. What did you do to introduce the scales?
Defined by the times.
By the
Time differences.
oh, just time differences.
That's all.
Oh, all right.
So you choose the ends in this geometric way.
Yes.
Yeah, you sum over all ends and then free
Yeah.
choice your
That's a choice.
Overall possibilities.
Yeah.
I mean, apparently the m's grow exponentially, which
No, that defines the j's instead of.
That defines the j. I mean, if m1, if the time difference is of order j, so it's just drawing. But I put it on the jth line. It's just a drawing. But I have to sum over all possible time differences, m1 and m2 minus m1, etc. And that's just a way of drawing things. That's a way. Okay. So you want to sum over m1, right? So what is the order of magnitude of this? Okay. Essentially, this is a local insertion, local in time at least. So it's lambda, maybe O lambda, something like this. Here it's like a propagator, of course, nonlinear propagator, but more or less this looks like a heat kernel. Okay. So you want to compose a heat kernel from t to t minus m1. And then you want to compose it with this heat kernel. So it's a convolution essentially. T minus m1, t minus m2. And then you want to sum over time in all possible values of m1. Right? More or less. So, as well known, this is simply.
Sorry, didn't you have the subtraction between t minus m1 and t minus m2?
The subtraction is, well, these are composed maps. Okay, it's a little bit complicated, but essentially it's of order lambda for me. So you add up a coefficient lambda in front.
Ah.
Okay.
Oh.
It's not very precise, of course, but I'm just explaining the renormalization stuff. Why we need a renormalization, which is basically understood by everybody, but. Yeah, so basically, you have something that looks like heat kernel, and then you do something of order 1 or lambda. And then again, which is essentially local, because it acts on a small amount of time, okay? And then again, you have a heat kernel, something that looks like it's dominated by a heat kernel, okay? So this is pt t minus m2, so it's m1 independent, of course. So the problem, if you sum over m1, you get something that is infinity, essentially. That is O of m2, and since m2 can be arbitrarily large, this is essentially infinity. Okay? So the problem is, this is where a renormalization enters in. So the idea of renormalization is to take the local part of the subtraction. Okay? If you take the local part, then essentially this will introduce supplementary gradients here.
Sorry, I don't understand your arithmetic there. When you sum, you have a sum over something that doesn't depend on the index. Don't you? Or do you get order m2? I mean,
simply
don't depend on m1.
M1? No, sure. That is a trivial sum. Totally trivial. Okay. Yeah. So where was I? Yeah. So assume that you subtract the local part. You have to renormalize coefficients. Okay. What the remainder induces a supplementary gradient. Now, how many gradients do you need? Well, one is not enough because, as you know from parabolic estimates, a gradient is just equivalent to t to the minus 1/2. Okay, or m to order minus 1/2. But here it's of order m, so you need 3 gradients essentially. Or 2 is not sufficient. That would induce a logarithmic divergence. So you need 3 gradients. So you need to renormalize to order 2, something like this. So assuming this is true, so you may.
So these are what kind of gradients are you talking about in time or?
No, gradients in space. Gradient is space gradient usually. So each gradient is like each gradient squared, if you want, is like a time derivative, more or less.
Oh, okay.
So 2 gradients are equivalent to 1 time derivative, which is obviously not enough to beat this divergence. So we need 2, or 3 space gradients are also enough. Okay.
Did you say again where the gradient came from?
I'll explain that more precisely in 10 minutes. Okay. From taking local parts. Taylor expansion of divergent diagrams. Okay.
Jeremie, so there is the step where you have the subtraction and there is the axis of time, and it seems that they're both at the same time t minus m1. Why did you leave a space there?
Okay, that's t minus m1 minus 1 maybe.
Oh.
Okay, correct. Right, so all this is well-known stuff from the 80s, more or less. I mean, Kupiainen has been doing this kind of things, and well, it's rephrased in a different way, but okay, wait. So now let me. What time is it? Okay. Try to describe more precisely the KPZ equation. Okay. It's much simpler, and fortunately, you want to have. I will be able to be much more precise and then I will end up with having linear flows. But it's much simpler. Why is it so? Because if I consider the KPZ equation with v of grade h equals grade h squared divided by 2, something like this. So let me just write down the equation. No, it's here, so no problem. This equation, okay? So I forget about this. Let me be very specific. Okay, so now what is well known is that if you take a Kolhoff transformation, so you replace h by w, which is exponential lambda h, basically, then you end up having a linear equation of this type with a multiplicative noise, which is linear. So that can be solved formally using, the Brownian motion, so averaging over trajectories of Brownian motion. So it's very well known. And so you have a random resolvent which I called g eta, which means simply that w t is g eta of t prime w t prime. And this time g eta is linear. Let me insist on this. Okay. And now if you want to solve the original KPZ equation, you need to take logs, which is not as trivial as you might imagine, by the way. That's part of the interest of the story. So this kind of random resolvents is a fairly standard and important problem in statistical physics. So, my article with Jacques arose of an old article he wrote with Daniel Jagonitzer in the 80s. Which was about weakly avoiding random walks. Let me just say a few words on that. Okay. It's a pity that so formally, so weakly avoiding random walks, and in 4 dimensions, so just in a just renormalizable dimension. So basically, you consider the Wiener measure, okay, and you multiply it by a certain weight, which is of this form. So essentially, you look at the self-intersection time of the trajectory. And you would like to put minus infinity in front, but you're not able to do this. You want them not to cross, not to intersect with themselves. But so you just put in some coefficient g squared and assume, well, let's call it just lambda. So lambda is small, as in my whole story. And then you can rephrase this in terms of random resolvent. So I don't want to make the derivation because I want to speak about KPZ equation, but this is more or less equivalent to the study of a resultant of this type. Laplacian minus Laplacian plus I square root of lambda eta, where eta is space white noise. So it looks very much like this problem, indeed. So there's no time dependence, but you could have added time dependence here if you wanted to look at time behavioral trajectories. But there's a huge difference, as in the case of the Anderson model versus KPZ equation also, that this is only space dependent, not time dependent. And there's an I. So it's more difficult because it's only space dependent, as in the Anderson model. But it's much easier because there's an I, analytically. So the denominator seldom vanishes, okay? Here you don't have an I, which makes it more difficult, but eta is space-time white noise, which makes it makes it so more regular in some sense.
that approach was really started by Sam Edwards in his original work on the Edwards model for polymers. This resolvent stuff.
Yeah, what was used by?
Edwards.
Yeah.
Before Lisa.
Yeah, I know, it's an old story.
In the early days.
Yeah, it's in the early days. And now if you... Then the list does not stop there, of course. I mean, if you look at the Anderson model of electrons in a random potential, you will also have something like this. So, well, it's a long story, and there are many interesting models with the same logic, but every time it's a little bit different. Yeah, so what is the statement? So what did we prove? First of all, as you know from previous talks, you have to recenter the interface, right? So it describes the upward motion of an interface. You don't want to flow it to flow upwards. You have to subtract some velocity minus v. So v is just a constant, but you fix it so that the average of expectation of h does not depend on t. Okay. So theorem. So for chosen v, then the following is true. So h. So if you take the product, let's say in this way. So well, if you have to be a little bit more precise, but it's not exactly connected expectation or truncated expectation, but it could be. It's, well, there's some subtleties, but you could see it as some truncated expectation. So you take the measure, the average, okay, just write it down with the physicist notation, but it depends on lambda, of course, right? So this is equivalent in the large scale limit, by which I mean that I choose all ti's and xi's to be different one from the other, and I assume that ty, the differences between ti, xi, and tj, xj go to infinity in a parabolic scaling. Okay, you all know that. So this behaves in this large scale limit like the product of h, ti, xi, but with a different measure, which is the measure. So here you have the original parameters, nu. What were the parameters? So we have nu. Okay. So let me call it nu naught. Because this is a bare diffusivity. Okay. Here, lambda is not renormalized. So this is d0, and this you might call v0. Okay. So here you have nu 0, d0, and v0. So with the original equation with the bare coefficients. So this behaves like the Edwards-Wilkinson solution since lambda is equal to 0, okay? And now with renormalized coefficients that I call nu f, like effective, and d effective, and, well, v is 0 in that case, okay? With nu f equal to nu 0 plus O of lambda square, and same for df. d0 plus O of lambda square. So this is the statement. So the logic is that of multiscale expansion. But it's very particular in the sense that the only random field here is ultra-local. It's eta. So you don't really need a cluster expansion for eta in the sense that it has a delta kernel, right? So you can prove that in that case, renormalization, so in contrast to this general setting and in a much simpler way, but technically you're a little bit involved, the only subtraction you need are at scale 0. So just for between t minus m and t minus m minus 1. That's the only thing you need, okay? No further subtraction, okay? So actually, nu f in Wilson's logic would be the limit of nu j of running constants for j going to infinity, but actually it's also equal to nu 1, just one scale, one renormalization step. And same for df, it's just t1, okay? Which the thing's simpler. Of course, this would be wrong, totally wrong for the generalized KPZ equation with the generalized with an arbitrary v, well, non-linearity, since you cannot rewrite it in this way. So then you would have to make the whole-fledged multiscale expansion. So that makes the model rather easy. So let me just give you some details about the proof, some ideas. Is that the correct time? So I have 10 minutes, more or less.
Well, you started perhaps 5 minutes late, so.
Okay.
10 minutes also good because I'm there.
Yeah, sure. Yeah, I think it's fine. So what are the different steps? One of the steps is the multiscale decomposition of propagators. So what is going to follow is really specific to this model now. Okay, no more philosophy. So for eta equals 0, the random resultant is simply the heat kernel. This is the heat kernel. Okay. Now, if you want to expand g eta, you have the resultant equation, which says that g eta is equal to g, or g0 if you want, plus g0 lambda eta g eta, and you can expand this, of course. So in the end, you will get a drawing that looks like this one, but it's much simpler. You would have first g0, so between time t and time t minus m1 if you want, then a totally local insertion, lambda eta is really local, okay? And then g0, and then again lambda eta, so between time t minus m1 and time t minus m2. Then another insertion at time minus m2, and etc. Well, it's a sum, of course, of all possible insertions. Okay. So now I need a multiscale expansion. So I'm going to write G or G0 if you want.
So you have now two lambdas. One is the coupling constant of the nonlinear term, and now the noise also has a lambda.
No.
Well, eta I thought was the noise.
No, because if you, okay, you don't have the equation with W anymore. Where is it? Okay, it's, okay, this is because dt minus delta W is equal to lambda eta W. The D coefficient has dropped off the equation because I was lazy to write it.
That's not your original lambda, I guess.
Yes, it is. Or maybe lambda times square root of D or something like this. But D is over to 1, so...
Because you now go to this Carl Hop
exactly.
description.
Okay. And so I want to write G0 as a sum of Gj, so the scale J, right? Where Gj is essentially, I rewrite it as product of two square roots. You will see in a moment why. So this is Aj and Bj, where in principle Aj is equal to Bj, of course. But so actually not exactly, but you may write down the formula for this. So this is the heat kernel, right? Then you have a cutoff, which selects time differences of order 2 to the j, but in a smooth way. And then you have 2 to minus j over 2, because when it's squared, that gives you 2 to minus j, and then it's time convolution, then you integrate with respect to time a constant, that it gives you back 2 to the j. So this is over to 1 in the end. Right, so the difference is I want these the Aj and Bk not to contract. These will be new propagators if you want. And I don't want the possibility that Aj contracts to Bk. If k is different from j, of course. So what I do is I rewrite it in a quantum mechanical way, just a fancy way of writing things, but you make n independent copies of your original Hilbert space, and well, you write in this way. So okay, well, it's not an important detail. So what's the main idea you already had? So what about this? A subtraction I was speaking about. So how come you have gradients? You remember Stefan asked me, why do you have gradients here, right? So let me just give you one possible Feynman diagram for this. So okay, what are these? So straight lines are simple heat kernels, right? So a half line here is like an eta, okay? So then they contract, but it's delta correlated, or almost delta correlated, since you have a cutoff at k0, but it's almost. So this is a contraction of two etas. So this is essentially delta. Okay, so these 2 points are essentially the same one. Not exactly, but almost. Okay. And this is missing. And what you see is something extremely important in this story, is that you have a causality property. So you have propagators from time t to time t prime, and they go backwards in time, right? And around those propagators, you have etas, dangling eta ends, if you want, that in the end contract. But here you have the main story is a causal story, right? That prevents accumulation of low momentum fields for experts. Accumulation of low momentum fields. Well, that's only for experts, but this is a very important part of the story. So this you may call a sigma of x times y, okay? So, but now what I really want to consider is the sum of all possible two-point function diagrams. And I call it sigma. Let me be imprecise at this step. It doesn't really matter. It could be just this diagram or the sum of all possible diagrams. Doesn't really matter. So I made Fourier transform it. And as you know, from quantum field theory, this is sigma of 0 plus p sigma prime to 0 plus p squared sigma secant 0 plus remainder. Right. So the way we do it in a real space renormalization is that we displace this leg to this space location. So we write, so here you will have a new propagator, okay? Here you have a new propagator, and you have a g something like this, g0 between t, y, and some extra vertex here. And so you rewrite it as g0 between tx and something. And here you have the difference between tx and t prime y. And this is small, essentially, because these two locations are within a diagram of scale 0. And since you have time decay at scale 1, they, with high probability, I mean, x and y will be very close, and t prime will be very close. That's for sure. But the x and y will be very close also. On the other hand, when you perform the subtraction, that introduces a gradient that may be made to act on the lower g0, maybe of arbitrary low scale, and that gives you a small coefficient with respect to the O of 1 x minus y coefficient that you had. This is the logic. Right, so I think it's about time. Probably you have questions. So let me just say in a few words how we do. So if you just wanted to study this field W, okay, so the exponential of the KPZ solution, that would be essentially the end of the story. The rest is more or less standard, so you need cluster expansions, but only at scale 0, okay, high scale. And, well, you need some vertical expansion. That's also for experts, it takes some time. But essentially, you will renormalize coefficients. That's a long story. It requires a few hours. It's more or less straightforward for experts. So it means that, well, you have to add and subtract some scale 1 effective theory with nu f minus nu 0 Laplacian or thing like this. Okay. What's original here is that you really want to consider cluster derivatives or any kind of derivative, also simple gradients, okay? Okay, but acting on not on W, but on the things you had in the beginning, which are log of W, okay? So if you take derivatives acting on log of W, this introduces the denominators, of course. D log W is W prime divided by W. So if you look at this, the problem is that you will get a terrible expansion with numerators and denominators. And the denominator is not necessarily large, or of the form 1 plus something. It might be of the type 1 minus something, and be arbitrarily close to 0, okay? So what do we do? Well, all this can be resummed using a trick that was used by Jagolnitzer and Mania originally, that holds for any problem of resolvents. So we made resum all these derivatives by using a sort of formal contour deformation in some parameters gamma, which are conjugate to those insertions, to these vertex insertions. It looks fancy, but it's not so difficult. It's not like considering this. It's not like considering this equation with in imaginary time, which you imagine could be terrible, because you only make the contour deformation act on things that are already integrated in time. So instead of having a local perturbation of the form pt minus t prime or something, you have something like I gamma pt minus t prime or something, and this can be summed. These are just formal coefficients. And so in the end, well, if you're clever enough, depending on large scale of large deviations for this field eta, you may prove that in effect in a given region of etas, for eta of order 1 or maybe large, but depending on that, you may choose the radius of the contour deformation depending on this order of magnitude of eta in such a way that these denominators are really of order 1 and cannot be arbitrarily small. And so in the end, you may resum over all possible regions in eta and all possible cluster forests. That's roughly the story. Thank you.
Jeremie, are there questions?
Yeah.
If you were contracting your wiggly lines,
Yeah.
you said they were almost deltas.
Yeah.
What kind of diagram do you have overall with this causality constraint? Could you just give you some examples?
Well, it's just as you
Draw a few.
it's just like 5-4 theory essentially. That is simply, well, if you really contract them.
I understand that, but you said there was a constraint on the time thing.
Sure.
Causality one.
But you can always take.
The same?
I think they're exactly the same. So if you take 5-4 theory and you split vertices into two halves and ingeniously, then you will always have this causality. These are really in one-one correspondence.
Could you explain your theorem again? So what's the weakly line, for instance?
Sure.
And it seems
So
that
you have to
on one
rescale.
side you have a lambda, on the other side you have no coupling. So is this saying?
Yeah. So let me be more precise. So you fix time and space coordinates ti, xi, that distinct one from the other, right?
You want the scaling, or is it the 1 and the 2?
Yeah.
Sorry.
The scaling doesn't look good to me with the epsilon.
It's not the end of the story, okay?
No, the upstairs.
Oh yeah, sorry. Yeah. Sorry.
Yeah.
You're right.
No, I wouldn't.
Is that what you meant? It's a parabolic scaling.
The first line was wrong with the exponents. The second line you make now worse than it was before, I think. Well, maybe okay.
No, I think it's correct. So you rescale them by epsilon in a parabolic scaling, and that's the main term in an epsilon expansion.
So then
I would have thought you multiply by a certain inverse power of epsilon in the first line, and then you converge towards what you had before.
Yeah, if you want. So this is scale invariant, of course. So you may just take out these out of the expectation, and that gives you epsilon to a certain power, which is the scaling dimension of the field.
Then it looks like a stronger statement because there is a power of 1 over epsilon involved.
Yeah, sure. So this is a symbol. I think it's 1 minus 1/2 of t over 2 minus 1 to the power n. I think it should be that. H T I X I. So you like it better this way.
So you start with initial condition 0.
Yeah. So either 0 or compactly supported. So actually, compactly supported in L1 and L infinity. Smooth.
The signs are exactly wrong on the last line. It should be epsilon to the plus 1.
Yeah, I think so.
Yes.
Yeah.
So
Yeah.
are you allowed to divide then by this?
Yeah,
epsilon?
exactly.
Or,
That's
I mean,
right.
the error is then also divided by the epsilon.
Yeah, but it remains uniform in epsilon.
Yeah,
Idea.
and so the next error term is in compared to this is in O of epsilon, something like this.
So you have convergence in the sense of moments, but can you turn it into convergence, reconvergence of probability measures?
Sure, that's. I didn't think about it properly. I must confess. So for that, so certainly you have a tightness in some sense. So you can use standard criteria by Billingsley or any. And in the end, it boils down to the question: do a finite distribution characterize a measure? So you see what I mean?
But finite moments may not
Yeah, finite moments, do they characterize? It depends on the large deviations of your quantities. It depends on the Q of distribution Q, tail. And I think it should.
I mean, that's a property of the Gaussian theory, right?
Since it's ultimately Gaussian, it should be easy, no problem, I imagine. But of course, the original theory is not. So, I mean, the answer is certainly yes, but I didn't think about it properly.
And how does the result compare to the one by Lanier and Alpha?
Yeah, so there was, I should have mentioned it before, so there was an article written almost contemporaneously by Rijik, Gu, and Zeytouni, so we spoke about it together. And so they used a very completed orthogonal method. So they started from the same equation basically, but they looked only at a W essentially, or directed polymers, or it's more general than my story in some sense. But essentially they look at W, and they get estimates in the end for W. But they do not translate directly to this. We discussed this with them, because they took W minus 1 divided by the epsilon. Well, I don't remember precisely. I mean, it's the problem with W is much easier, as I said, in my way of seeing things, and you cannot translate the estimates they get, the leading order estimates, to this, which are estimates on log. It's more difficult. And they didn't. They told me they didn't know how to obtain my result using that. It was based on a very clever Ito representation or Ito formula, explicit representations, and argument I do not really understand. The probabilistic arguments.
Yeah, I think we should just stop here perhaps. Let's thank Jeremie again.